You cut me off. Oh.
Good afternoon, Mr.
Hello.
Can you hear me?
If you are
Hello?
speaking, I'm not able to
I'm
hear. So
Oh.
just a moment, let me check my sound settings. These days, my sound settings are an issue, serious issue. But let me just check it out. So they're trying to, okay, maybe I should hear you by now.
Hello?
Yet
Oh.
nothing. Hello? Is my mic on?
Hello?
I might be mute myself. Okay, my mic is on. Okay, you're saying
Hello?
something on the chat. I am speaking, I spoke. Hello. Okay, very good. What seems to be the problem with the sound? Again, okay. This thing is definitely trying to put out sound from the headphones. There are no headphones. Okay, just a moment. Let me try and turn something off here. Let's turn this off. Let's close that. I have a lot of apps or programs open. They might be the ones interfering, so I've closed that one. Sound mixer. Oh, it's so annoying, but you can hear me, obviously. Now, input devices, the mic. Okay, the output says here, speaker, headphones. Hello, can you say something?
Hello?
Okay, headphones obviously shouldn't work because that's not what I'm using. Now I'm using the speakers. And yet, let's see. Mute, unmute. This is so, are you sure your mic is on?
It is.
Let me just check. Mute, unmute. Can you unmute yourself?
Hello? Hello?
Yeah, can you say something?
Hello?
Hello. Okay. Oh God. Just a moment. I'm trying to troubleshoot. Okay, test mic. Testing my mic. My mic is on. So this is my input. Okay. I obviously can hear myself. Can you say something now again, Hosanna?
Hello?
Excellent. Now I can hear you. Very good.
Hello?
Oh, sorry for that.
It's okay.
So let's just delve into.
Mister. from the problems that I sent you, majority of them, my teacher, he actually hasn't taught us anything. I tried to read upon it, but he hasn't taught us the material. That is why it was difficult to understand.
I understand, but let's try. He hasn't yet taught, right?
No, he hasn't started, but like I want to get these problems like over with, so I want to do them.
That's not a problem. I've tried to solve them, so we'll go over them together, and then you will just have them in your notes, you know. So as he teaches them, you'll just be reinforcing, you know, strengthening
Yeah.
any weak points, you know. You can always come back also. So it's not a loss. It's not a loss. Actually, it's a win when you go into class, you know, ready. Although you have to fight the urge to interrupt as he tries to teach and solve,
Yeah.
right? You will have to,
Yeah.
by all means, pretend you are seeing them for the first time. Okay?
Yeah.
That unless he asks you directly a question or asks for someone's participation, you will be able to give modest participation as if you are not prepared, because once the teacher feels that you have prior knowledge, he may come in or come on hard on you, right?
Yeah.
Start expecting more than you can deliver. So by all means, we'll go over them. You will take notes. You know, you will store whatever you can store. You will memorize, learn, but by all means, do not try to show the teacher that you know. It's like going to a driving school and then telling the instructor that you've driven before. It's not good. Usually doesn't bear good results. So let's move on. Let's move on to the problems. As I said, try to solve them. So we start with problem 9. You can see the screen. Am I sharing the screen right now? Yes, I am.
Yeah, I can read. A mass M is located at a distance d from the center of a planet. It experienced a gravitational field strength of G. What is the gravitational field strength experienced by an object of mass 2m at a distance of d/2 from the center of the same planet? Give your answers in terms of G.
Excellent. Let's try this one. So, for this one, we'll have to go to the blue screen. We'll open a blue screen. But you know, even if he hasn't taught, one thing for sure, you know Newton's universal gravitational law, right?
Yeah.
You know it by heart. By now, you really know that. You know, you can be woken up and asked to solve it. You at least write down the equation. You are able to do that. So that's the key, really. Nothing special in this, rather than remembering that Newton's gravitational law of motion and of course Kepler's 3 laws, you know, to enunciate them, to know them, plus a series of laws that you should know by now, like for example, circular motion, the notion of angular velocity, acceleration, you know, linear velocity, the differences and the angles, the radians, so on and so forth. You combine all those and you can be able to surf through this topic of gravitational field and circular motion. So the radius of the Earth, no, this is not the one I've just opened. So you say the mass M is located at a distance d from the center. That's what you read, right?
Yeah. D from the center.
Yeah, okay. That's problem 9. A mass M moves. Okay. All right, we can solve this one quickly. We can solve this one quickly, even though the screen I just opened is not the one. So let me just stop sharing this and create a new blue screen and share that blue screen. I'm sorry for the time, for the delay. Okay, you can see this blue screen, right?
Yes, now you can.
Now you can see. So we have the enunciation. You've read it. It's not bad to copy it, but I hate the hassle of copying it again, but okay, it's good for us to have it here. All right, so here it is. So what do they want? They want us to determine what is the gravitational field strength, right? So
Yeah.
as we said, you already know that I'm writing without a pen currently. My pen is not being connected. Now I realize that because Bluetooth is not on, I feel so clumsy. Anyway, you are aware. Excellent, now I'm connected. Come on, pen, come on.
The Bluetooth device is connected successfully.
That's okay. What's wrong here? Am I without battery? Okay, so you know that there's this equation. It relates the mass m and then relates it to the mass of the planet P all over the gravitational field strength G. What is the gravitational field strength? Okay, so it experiences the gravitational field G. What is the gravitational strength experienced by an object 2m at a distance? Okay, first, this one will be at a distance of D. So it's a matter of using different letters. I'm a little bit concerned with my writing pad. Just a moment. Let me just confirm what's going on here. Okay, it says I'm connected. So why? Oh, technology is doing what technology does when technology wants to complicate your life. So let me just deal with this. I think my drawing pad is without battery, which is strange because I charged it, but I will soon be able to. All right. Oh, you saw that? Okay, so you know this is Newton's universal gravitational law, but again, the mass m is also related, being located at a distance from the center of the planet, it's also related to its mass, the mass m, and then experiencing a gravitational field strength, which is G. So these two are related in a normal situation. And from these two, what is the gravitational field strength? So they want G. So for this case, G will be given by us equating these two. So we can say mg will be equal to G of m of the planet, and then the distance squared, because both of them are equal to F, correct? They're equal to the force generated by such a gravitational field strength. So we can equate whenever we have F is equal to something and F is equal to something, it means those somethings are both equal, correct?
Yes. So if you have the
So that's why we could take this and put it here, and we took this and placed it here.
Isn't that weight?
That's very important.
Weight? That becomes weight, doesn't it? Like mg is weight.
Mg, technically it's weight, we know it as weight, but now we are using different language. We call G gravitational field strength. When you multiply by the mass, indeed, you get weight, which is a force. So we can call it a force due to gravity. Now, why are we here? Because we want to express, as they told us, what is the gravitational field strength. So now, here, if we could express all of this in G, we will say mg being equal to G times m of the planet all over the distance squared. We will just remove the m, divide m both sides, right?
Yeah, so you can just cancel m.
You got it. We divide by m, so m disappears. So in the end, we will express, for the first case, we will say the gravitational field strength, which is G, will be equal to the gravitational constant, the universal one, capital letter G,
Yeah.
times the mass of the planet in question, all over the distance squared. So this is for this first case scenario. Now the question says, what is the gravitational field strength experienced by an object of mass 2m? So now we move on to our second scenario. I will copy these because I will need it. So in our second scenario, instead of F is equal to m, we have F is equal to 2m, right? That is the mass of this object, and will be equal to a certain G. Again, we know that since it's related to the planet, we can also say F is given by capital letter G, and then the mass of the object, which will be again 2m,
And
and
then
then related to the mass of the planet,
over the
all
radius
over.
squared
What about the distance now? What is the distance given to us?
is half of the distance, so can be
Excellent. So it's D over
divided by
2. So we can equate both of these just as we did before. 2mg will be equal to, we could choose to put 2gm and then mp, mass of the planet. And then because of the reciprocals, we know what these two can do, right? Can't these two be taken up?
yeah. Pardon?
So if we do that, this is a matter of just, it's purely mathematical. So these two here that I'm erasing will be
Oh,
multiplied.
I can't see your screen anymore. Like whatever, if you're typing anything, I can't see it.
You can't see my screen.
Okay, now I can, but like it was like I
Oh,
couldn't
okay.
see
So
it.
here we will put the D here. However, the 2
Yeah.
will bring it up and it will interact with these 2.
Yeah.
So that we will have 4, right?
4, yeah.
You got it?
I did.
Now,
Mm,
let's do the next phase of the problem where we try to divide anything that is repeated. We remove all repetitions. What is repeated in this equation that can be divided both sides and disappear?
2 and m.
Excellent. So we could say divide by 2m. So here m will go, and then here in the 4, one of the 2's will go, right?
Yeah.
And then we'll get this. And therefore, this leads us to G will be equal to
2G
capital,
DD.
come again?
2G equals MP over D.
Excellent. Oh, sorry. This was squared. Oh my goodness. How could we let this go? Yeah, we almost oh, I just remember now. Okay, let's do it again. Let's do it again. You see,
Okay,
that's where the student lags behind. You know, that's where we start failing when we know, right?
Oh my God.
So here will be D squared. But what about 2 squared? What is 2 squared?
4.
So we multiply 4 by these 2. What we get?
8.
Excellent. So that we had to fix that. So again, we come here, 2 goes away, but now here we had 8. 2 will go. You get what we're doing, obviously. So what we have here instead of 2?
So it's just gonna be 4 GMP over D.
Excellent.
It's gonna be the original.
It's gonna be 4. It's gonna be 4. Yeah. So here it's gonna be, so I'm just fixing it. So here we will still have a square as well as here. So now we will carry on with 4, right?
Yeah.
Now, the English that you used here, they said, give your answer in terms of what?
G. So it's gonna be
So
it could be that.
what it means, So this is where you have to be careful. Let's zoom out a little bit. So in the first instance, we left everything in terms of G, right?
Yeah.
Here at 1. So now we're at 2. So let's call this one, the second G, let's call it G prime, okay?
Okay.
So what they want you to say G over G prime. Actually, you can even say G prime over G. It will always give you the same relation. So what is G all equal to, according to 1?
G is equal to GMP over D squared.
Excellent. So what about G prime?
Ooh. G prime is 4GMP over D squared.
Excellent. You know, here it's almost about mathematics,
have
you know, and semantics.
They have the same denominator, like both.
Excellent. So so you can see. So what can we do here? If we have all these repetitions, what do we do?
You can just like put the denominator, yeah, and then just cancel them out.
Everything that is on the numerator and the denominator goes, right?
So G is just gonna be 4.
Yeah. But be careful, not just 4. So because we're dividing. So G divided by G gives us 1, right?
Yeah.
MP divided by MP gives us 1. D squared divided by D squared gives us what?
But you're
1.
give you 1,
So,
yeah, but you're timing it, so it's still gonna
so
be
what happens at the numerator? What you get?
1.
1 times 1 times 1, what do you get?
1. It's still 1.
Excellent.
So it's
What about the denominator?
It's gonna be 4 over 1, which is 4.
Anyway, take it easy, take it slowly so we can be sure.
Okay.
So G will be equal to 1, while G prime will be equal to 4. So what relationship can you say here? So what is G prime equal to? So here we could have chosen to put G prime on top. I continue saying probably the answer will be the same. We can actually test it. But anyway, what do we do here when we come to a situation like this? What is the tool of mathematics you use? Start with a C.
I don't do calculus yet.
No problem. So you cross multiply, right?
Oh, sorry. So 4G.
So what do you get? Exactly. So G prime will be equal to what?
I mean 4. Well,
No, you
no,
said
1,
it. You
1,
said
1,
it
1.
correctly.
Sorry.
No,
1,
say it
and then
again. You said it first.
Yeah.
G prime
equal to 1.
Equal to what?
Equal to 1, and 4.
Look at the cross multiplication. The cross multiplication helps you.
G prime is equal to 1 in that regard. Like if you cross multiply.
No, G prime. Well, let me explain. When you cross multiply, you say G prime times 1, so you get a G, right? You get a G prime, right?
Okay.
Right? So this is why you get a G prime. It's actually 1 times G prime, which is G prime. So what about the other side of the equation? What do you get?
It's 4.
For what?
4G.
Excellent. You said it. I heard you say 4G. Then you started wondering. But you said 4G. So what they want you to say, it's okay. The new field, gravitational field strength in terms of G will simply be equal to the 4 times the initial due to the different circumstances. You know, now the different circumstances was that the distance had been halved, right?
Yes.
And which makes sense. If you make the distance half, what happens? You lose, you gain what? If the distance is shorter between two bodies, what happens to gravity?
It's stronger.
Excellent. So this answer makes sense. So, excuse me, I'm saving this so that I can send it to you. This is exercise. Actually, it's the correct exercise 9. Oh, please. It's exercise.9 underscore so that it doesn't destroy it. I will send to you just as we do. So let's move on to the next problem. So we stop sharing this screen and we share our presentation of the next problem. The next problem reads, can you read the next problem? This one was quite hard, but we'll see.
A spacecraft traveling from Earth to the moon at point P. The spacecraft experiences no resultant gravitational field strength. If P is at x times 10 to the power of 6 from the center of the Earth, what is the value of x? Use the data below to get to 3 significant figures.
It's a very hard problem. We'll start it. We may not finish it because it's got a lot of math which you have to deal with. But let's tackle it. So it's problem number 13, exercise 13. Let's tackle it. Where are you? Exercise 13. So first I have to pop open exercise 13. And then as I seek to share, I have to go back. Okay, close this. Reshare exercise 13. So you can see the blue screen right now, right?
Yes, I can.
Yeah. So this one indeed is quite a tricky problem. What we have here is a situation where we have the Earth, we'll call it E, and then we have the moon, very tiny here, M, right? And
Yes.
they tell us the distance between the Earth and the moon. What is it? It's 3.84 times 10 to the 8 meters, right?
Yeah.
Agree? Now, they tell us that as the spacecraft travels from the Earth to the moon, there is a point in which the spacecraft experiences no resultant gravitational field strength. Now, you remember forces. When the resultant force was 0, what we call that situation? When the net force is 0.
I don't know.
Remember, look, let's remind you. When the net force, because the net force will be the force due to the Earth plus the force due to the moon. Now, it's interesting for us to remember that these forces are antagonistical, right? So we could put a minus here. You know, they are acting, one is pulling to each other, right? To itself. Like the Earth pulls it to itself, while the moon does that. But what happens as you travel from the Earth to the moon? What happens to the force exerted by the Earth? As you move away from the Earth, what happens to the force it exerts?
It becomes weaker because it's further away.
It what? Yeah, now I'm not hearing you. I can hear you from far.
It becomes weaker because it's further away.
Yeah, you are right. Correct. So I've drawn it here. So this represents the force from the gravitation of the Earth getting weaker. But at the same time, when you move from the moon, what happened to its already weak gravity? As you move away from the moon, what happens to it? As you travel to the Earth from the moon, what happens to the gravitation of the moon?
It becomes stronger.
I'm saying you have gravity on the moon. It's weaker, but it's there. Now, as you move away from the moon, what happens to its gravity?
I thought if you move away from the moon, it's like basically non-existent.
Well, moon has got gravity. What happens as you move away from the gravity? Just like from the Earth, what happens when you move away from the moon?
It becomes weaker.
Excellent. That's it. Same. The moon is a celestial body. It's a mass also. So it becomes weaker, right?
Yeah.
You follow, right?
I follow it. If you go further away, it's weaker.
Now,
because
it's important for you to follow because, you know, at this phase of the problem, we are like doing the analysis, you know, so that even when you are alone, you know how to analyze these problems. Now, there is a point where the strength of gravity exerted by the moon will be equal to the strength of gravity exerted by the Earth. Do you agree? As you see these graphs. So
Yeah, that is true.
at this point here, graphically speaking, of course, this is not drawn to scale, right?
Obviously.
It's just a representation. Now, at this point, when both of the forces, you know, are equal, of course, what is the value of the net force?
0.
Come again, say it loud.
0.
Excellent. 0. Don't be afraid to make mistakes. So in this point, the force is 0, which then mathematically leads us, and actually graphically, leads us to realize that, okay, at this point, when the gravitational field, we call this point P as the problem wants us to call it. At point P, the force exerted by the Earth will be equal to the force exerted by the moon. You see, they are opposite. One is negative, the other is positive, because they're pulling in opposite directions. So now what the problem wants us is to find at which point this happens. We don't know, but we have data. We have the distance, the total distance, correct?
Yeah, we do. It's 3.
And we have at our disposal the knowledge of the equations applied in these systems. Let's consider the force acting on the spacecraft as the spacecraft leaves the Earth. We will call it force E. It will depend on the mass of the spacecraft. We'll call ms. And then it will depend on the G of the Earth. Right?
Yeah, I'm following.
Again, the same force can be expressed in terms of, can be expressed, again, we can express the force of gravity in terms of the mass of the Earth against the mass of the moon, depending on the D. Let me check my notes before mass of the planet, Earth, mass of the, okay, no, not, so it's mass of the particle that's moving. In this case, let's call it P, the space, let's call it S. We called it S here, let's call it S here. So it will be over the distance that we do not know. So now let's call this distance DE. So we'll call it distance in relation to the Earth. You agree?
I do.
So let's define what DE. DE is actually the distance from the Earth to the moon, which is 3.84 times 10 to the 8 meters. That's what DE is. Minus X. Minus X. The distance X. So the distance X will be the distance, the rest of the distance.
Why is it minus?
Sorry?
Why is it minus the distance X?
Yeah, because if the spaceship is here at P, we are talking about this distance. It's good. I like that question.
Okay,
it helps us to reason.
Okay.
So we are calling X, therefore, this distance, right? Right?
Yeah. Okay.
So this one will be. So this one will be DE.
Yeah.
So, okay, we have this. Now, we can equate these two just as we do. We'll say the mass of the spaceship, depending on the G of the Earth, all equals to the remove this. Will be equal to the mass of the Earth times the mass of the spaceship on this newtons. Oh, we missed the G here. Times the G. Yeah. Times the G divided by the DE squared. Of course, we know DE squared, DE is equal to 3.84 minus X. So we have this expression. Again, here, we can cancel MS, right? The mass of the spaceship is not necessary. And then we will have that G We can leave this in terms of what? Since we want dE, let's leave it in terms of dE. So let's do some math. We will have GE is equal to capital letter G, mass of the Earth, all divided by dE squared. But we are looking for dE squared, right? So we come here, we say dE squared will be equals to G. Help me out here.
D is equal to G. Wait, what? Over G.
Excellent. Over GE, which is G. We're still not done. So we find a square.
Yeah, the square root of all of that.
Yeah, square of this of G
What's the
M
mass?
E.
The
Yeah.
mass of Earth.
Now we are still not done because we know that GE represents something greater, represents all of this, right?
Oh my God.
So we say 384 times 10 to the 8 m minus x is equal to the square root of GE over G. Then we move on. We occupy some space here. We can take the x this side, right? So that it can become positive. So we say x will actually be equal to 3.84 to the power of 8 minus this whole argument for which we have the figures. So this is what we have. This is the first equation. Now we will do the same thing from the part of the moon. So we come back here. We did it for the spaceship leaving the Earth. So now we'll do it for the spaceship approaching the moon. First thing we will do is do this set of equation. Let's just copy to help our memory. Put it here. So we change it now. So we can call this, just a moment. Let me just erase this here. Erase this. Erase everything that has got to do with the Earth. So I want us to do something. We can call this equation 1. So now we're looking for equation 2. So for equation 2, we'll have the force related to the moon, this approaching the moon, as the spaceship approaches the moon. So we have to make this negative since it's approaching the moon. On the other side, we did it positive because it was leaving the Earth. We can't use the same sign. So let's put negative here, or either we put negative on the force itself. There has to be a negative sign. Otherwise, we'll have errors in our answers. Since this is approaching, the sign has to change. So again, it will be depending on the G of the moon. And here, let's find the distance. What is the distance? The distance is the X, right? Right?
Yeah, we're trying to find.
It's X. So the distance from here is the unknown distance. Actually, it's X. From P to the moon, it's X. So
I'm not.
We can directly put it. Come again?
Like I'm not following. Like this got way too complicated too quickly.
Yeah, I understand. I agree. But this is how we solve it. Actually, really, it's mostly mathematics rather than gravitational field. If you notice, we use Newton's law, first law of motion. Force is the second law. Force is equal to mass times acceleration, right? And then we use Newton's universal gravitational law, which is F is equal to G capital M1, M2 all over R squared. You know, it's the same. The only thing here was the analysis that you had to do. So the distance that we don't know is x. So let's write, hold on a little bit. Hang on a little bit. So now, this is FM again in relation to the moon. And then we equate these two. We say mass of the spaceship in relation to the G of the moon will be equal to G, universal G, and then M of the moon and mass of the spaceship all over the distance x squared. Now, we cancel what repeats here. We don't need this. And then we come here, what we have GM will be equal to G, capital letter M of the moon, all over x squared. What else can we do here? So we want x. We do that change, we swap, cross multiply. So we'll have that x squared will be equal to capital letter G M all over small letter G M, and then x therefore will be equal to square root of G times M, the moon, all over G M. Then after that, so we have the second equation. So this is equation number 2. How many unknowns do we have?
The x and
The x,
we have the mass of the earth, don't we? Only the x, no? Yeah, it's only the x.
what we don't have here is the G of the moon.
Oh, but we can calculate that.
Yeah, the G of the moon we don't have. Because at this moment, we could substitute x. If we only had x as an unknown and 2 equations, we could solve. We need a third equation. So what did I do different here? When I did it last time, I didn't have to consider the G of the moon. But that's why I didn't get the answer as I wanted it. Yeah, but the problem will be solved by doing this first analysis. But let's try. Now that we have this here, we have these 2 equations. What can we do? Minus GME over G. This is the G, because even in this problem, we're not given G. We know it's 9.8. But now, what is the G from the moon? That's an issue. But if we could substitute this X and put it here, both of them are equal to X. Ah, okay. Check this out. Let's try this. We have 2 unknowns and two equations. We should be able to solve. So let's do this. Let's take this and substitute it here for X, correct?
Okay.
So we'll take equation 2 and put it in equation 1. So instead of X here, instead of X, we'll put this argument that we got from, instead of X, we will put capital letter G, M of the moon, all over G, M. So now we have all known figures except GM. So we can find GM. So now it's a matter of us solving this. How can we solve it? There are many ways to solve it. This is mathematics right here.
Okay.
This is mathematics. Since
Well,
this is being added, let's just,
you
let's add it. Let's say square root of GM of Earth, GM plus square root of GM of G. This is G, this is normal G of the Earth, is all equal to 384 times 10 to the 8. So here, what can we do?
Yeah,
Square root of this or square root of this. We could square everything, right?
Yeah.
So you
can
grab your calculator. Can you square this number? You square this.
Wait. Which number? Oh, okay. Oh my god. 3.84 times 10 to the power 6 squared. Wait.
3.84 times to the 8 squared.
It's
3.84.
1.47.
1.47.
Yeah, times 10 to the power 13.
17, right?
13. 17.
Isn't it 8
No.
squared? All square. So you must be careful. Let me give you a tip.
Oh, 8.
It's okay. Can you do it
Yes,
again?
is 17. Yeah, 17.
Okay, so it is right. It is right.
Yes, it is. It is.
Okay, so now we do the next thing. These numbers, these figures represent known numbers. All of these, right? So we're looking
They
for
do.
this little guy here. Then we can be able to solve. So let's plug in all this data, all these numbers. So here, G we know is 6.67 times 10 to the minus 11, right?
Yeah.
Right? Times
Yes,
M,
yes, I'm following.
the mass of the Earth is 5.9 what? The mass of the Earth is 5.97 times 10 to the 24. Times 10 to the 24 power. Close this bracket and still respect that it's being dividing by the G of the moon. Plus, what is G again? G again, we know it. It's times 10 to the minus 11. Very small number. You said it before. The mass of the moon, the problem gives us as what? 7.35, right? To the 22. 7.35 times 10 to the 22 to the 22nd power all over G, which is 9.8, right? This is G from the Earth. All of these equates to 1.475, actually, 1.475 times 10 to the 17, right?
Yeah, 7.35.
So let's. So what you got? What you got here in the first one? So I normally when I multiply exponentials, hear me out. I normally do this in my calculator. I open a bracket, then I say 6.67, and then shift, 10x. So it will be minus 11. Close my bracket, multiply, open bracket by 5.97, and then shift exponential to the 24, close my bracket. Why I do this? And then equal. This gives me 3.98199 times 10 to the 14. I normally do it like this for safety, to safeguard something, because I believe that if you, so the other one gives you what?
The other one gave me 5.0025 times 10 to the power of 11.
It should give you 4.9. 4.9 times 10 to the, you know what happens? I'll explain to you. I was trying to explain it, to explain. Listen, when you type on the calculator, there is a risk. For example, for this case, there is a risk of your calculator thinking you're trying to tell it this. 6.67 times 10 to the minus 11. And check this out. Times 735 times 10 to the 20. So, oops, escape. So how would you avoid this? How do I avoid this? I open a bracket, I do this. It takes me a little bit of extra time, and then I close my bracket. Then multiply, open another bracket. The second bracket is optional, but I normally open it. Even so, you see. So why do I do this? It guarantees me that the calculator will treat this number entirely as a different number, and this one is a different number. You get it?
Okay.
Take that method to the exams. It will save you. Some calculators are funny like that. You see? Check, tell me, do you confirm the answer? Is it 4.9?
yes, it is.
Yeah. So now after this, again, you still equate it to 1.475 times 10 to the 17th power. So now we're still dealing with mathematics. Let's just fix this argument here. We divide this, right? And see what it gives us, correct?
Yeah. 4.9 times 10 to the power.
Still on our calculator, divide by 9.8. Oops, not 98,
That
9.8.
equals 5.
Oh.
5.0.
What do you get? What did he give you?
5
What did he
times
give you?
10 to the power of 11. 5
Excellent.
times
So
10 to the power
again,
of 11.
well, I might have to do it. So it's 3.98199 times 10 to the 14, all divided by the unknown G of the moon, plus, what did you get here? 5 point what?
10 to the power of 11.
5 point?
No, 5. Oh, times 10 to the power of 11. Like 5 straight,
Okay. Yeah. To the power of what?
11.
Excellent. I got you. So now we move on. We do our mathematics. So it's all about algebra. So we can say all of this number minus this 5, right?
Yeah.
1.475 to the power of 17 minus 5.0 to the power of 11. Boom.
That is
What do you get
equal-
right there?
I
Gives you what?
What? Wait. 5 times. I have to do it again. It gives me the exact same number.
Yeah, me too. Strange, right?
Very.
So it means that, well, this is positive, right?
It is. Yeah, I minused it. I know that for sure.
Me too. I minused it. Okay, let's trust the calculator. No. I think what happened is what I was telling you, I was warning you about. Let me open brackets, 1.475, you know? So I'm suspecting, okay, close brackets, minus open brackets, 5.0 to the power of what? Of 11, and then close my brackets. Oh, it gives you the same number. So it means that this 5.0 times 10 to the power of 11 is an infamously small number. This is very strange, huh? Okay. Let's leave it like that. That's what you get, right? But what are you left with here? You get what you're left with
exactly
here,
what I
right?
got.
Huh?
Okay. So then
So what do you do? What's the next move?
I divide 3.98 by the number.
Or you divide 1.4 divided by? Oh,
That's
no.
what I, yeah, that's
Let's
what
be
I,
careful. You're right. No, you are right. You divide 3.8 by, because you cross multiply. Excellent. This is over 1. So you cross multiply. So what you said is correct. It will lead you to multiply 3.8 times 1 divided by this. It's called the rule of X. So you're saying 3.98 times 10 to the 14, all divided by 1.75. You were just quicker. And then here, all of this will be equal to GM, right? What do you get?
I got 2 point, if you put it in scientific notation, I got 0.00698.
0.0?
0.02698.
2 zeros.
3 zeros. 3.
I'm tempted to do it. 9.
What? Oh no, that's not what I got.
So let me just do it.
I got
here.
0.00698.
Yeah, since I didn't hear you out quite clearly, loud and clearly, I've calculated it. Okay, so if you have a 269, it's correct. So it's 2.698 times 10, very small number, the minus 3, right?
Yeah.
Newton kg, if I'm not mistaken. This is the G in the moon. So we have this number. Let's hope it's correct. We come here, we substitute it to get X, right? It's the number that we need here, isn't it?
That's such
Here,
a long.
here.
Wait, let me put that.
Equation 2, right?
Yeah.
Oh, let me just copy
Wait,
equation
let me
2.
just-
This is equation 2. So we established equation 2. We were missing a value, so we have it now. So equation 2 was X, the distance X would be, so let's check if it was worth it. So now we say X will be equal to the total square root of G. G is 6.67 times 10 to the minus 11 times the mass of the moon. What is the mass of the moon? We come up here, it's 7.35 to the 22. 7.35 times 10 to the 22nd power. All of it over the number we've just calculated here. GM 2.698 times 10 to the minus 3. That will give us the distance. So what is the distance now? This is the moment of truth. Woo, the square root of all of that. So normally we will do it step by step. We're not rushing. Let's make this our last problem. I believe that we're out of time. So first, the numerator. What does the numerator give you?
Wait, I did it. I'm doing
6.67.
it. It's like
I open the brackets. 6.67. Oh, sorry, are you following?
Oh, the whole thing, like the square root of the whole thing gave me 4.26 times 10 to the power of 7. Like the square root X
Be
gave me that.
careful with the whole. How do you? Okay, let me not question your methods, because normally you're usually quick and successful in the speed. Let me just do it step by step. And then again, you have 2.698 times 10 to the minus 3. Still, divide the whole thing by 2.698 times 10 to the minus 3. So you get a 1.8. 1.817 times 10 to the 15th power. And finally, what is the square root of that? Square root of answer. Yeah, you said 4.2, right?
Yeah.
4. This is not, something is not right. I'm not confident, but anyway, times 10 to the minus 1, 2, 3, 10 to the 7th in meters. Why is this wrong? So they say they want it in terms of, you say 4.2, 42.6 times 10 to the 6th meters. I went wrong somewhere here. Why? Because if you come back here, what is the distance between the Earth and the Moon? Oh, it's 3.84 times 10 to the 8 meters, right?
Yeah.
You get it?
Did we get it wrong? Okay.
No, check. I wanted it to make sense. This is times 10 to the 8th.
Okay.
Our answer is less than that.
Wait,
It's 42
4 times.
times 10 to the 6. So let me check what I was expecting as an answer. The correct answer, the one that I was expecting, is somewhere around 3.46 times 10 to the 6.
Oh, that's what I got. That's what I got. I
You
got
got that when you
3.4
calculated?
when I minused it, but it wasn't. Oh, never mind. Never mind.
When
I
you
got
minused it from
3.4.
what?
When I minused the distance from the Earth to
From
the
the whole
moon
distance.
minus like this. Yeah.
Really? Let's check. Oh, that's good.
I mean that's
So it's a matter of coming back here.
Yeah,
Let me just check
that's
also if I get that. Minus the answer. Oh, yeah, I got 3.4. Yeah.
Yeah, me too.
Excellent. Remarkable.
Oh my God. I didn't get this problem at all, but I did get the answer. I'll need to go over it. Like actually, I need to sit down and think about it. 'Cause
I'll
this one
send
was
you
actually
the information so you can go over it. It's not an easy problem,
Mhm.
but anyway, we had to solve it.
Like,
We have other two, but the time is up, right? Right?
yeah, but
It's not much really.
like
And much of the problem really is mathematics.
which is
If you
no,
look at
it's-
it,
there,
with
there's a
distance,
lot.
you see?
There's lots of variables. That's the issue.
Yeah. Basically, you have two variables, but before you get to them, you have to do this analysis of the well, there are two equations, but then you have to repeat them twice because of the situation. Oh, yeah, moving on. Do we have time for one more?
If we can finish it in 9 minutes, then yeah. If we can't, then I don't think so.
9 minutes. Let me see which one it is so that we can. It's just the one of comparison, you know?
Okay.
Yeah, we probably can finish it in a very brief period of time. Okay, so let me just stop sharing this one and share it. Look, I still really need you to ask your mom to get in touch, right?
Yeah, but
You told me she's
currently
in Portugal, right?
in Portugal. Yeah.
She's in Portugal, right?
Yes, she is.
Actually, I want to talk to her about the I didn't want to involve you about Linguistica, you see? And last time we spoke, your mom wanted some. Come again?
Oh, no, I didn't say anything. Last time my mom said she
So I
wanted
was
some
saying, I wanted to speak to her about Linguistica. Plus, also your sister does she still need those lessons?
No, I don't think so, because the unit that she needed help with is already gone. So they're like, and my sister's here to go through like units are subjects. So her last unit was physics, so her new unit is like biology.
Okay, I get it. So now moving on, but yeah, I need to talk to her about perhaps our lessons because of Linguistica. There's an issue, the pending issue. Now, let's move on to this problem. A satellite orbits the Earth in a circular orbit at an altitude of 1 Earth radius. If the altitude of the satellite above the Earth's surface triples, by what factor will the orbital speed change? Orbital speed. So give your answer to one significant figure. Amazing. So now, first, they tell us a satellite orbits the Earth in a circular orbit at an altitude of 1 Earth radius. So let's have the Earth here. So this is our Earth. And then this is our Earth radius. We'll just call it capital letter R. And then they tell us that the satellite orbits at a height of what? Of R, right?
Yeah, the Earth's radius.
Here is our satellite. Now, it's orbiting at an orbit equal to the radius of the Earth. So the radius of the Earth is R, and then the satellite orbits at R. If the altitude of the satellite above triples, now, by what factor will the orbital speed change? So let's start with the first situation. we know that our satellite has got a mass and depends on G. G is an acceleration, right?
Yes, it is. Due to gravity. Any gravity.
So if it's an acceleration, so this is mass of the satellite. Mass of the satellite. So if it's G is an acceleration, it means that G is also equal to V squared over R for the first situation. And indeed, in the first situation,
Wait, it has
what
it's
is
the Earth.
what is R? Looking at the center of the Earth, our R will be 2R. Remember, the analysis is made assuming the distance from the center of the mass. So the center of the Earth
Yeah.
towards the surface of the Earth, the distance is R, correct?
Yes.
Then again, from the surface of the Earth to the height of the satellite, there's another R, correct?
Yes, sir. So it's
Therefore, 2R. So instead of R, this equation is normally F is equal to M times V squared over R because of angular motion, right? Radius. So that here we just changed and placed 2R. So it means that the speed now, let's express all of this as speed. We can do that by remembering again that the force will be depending on capital letter G, mass of the Earth, and then mass of the satellite, all depending on R. In this case, R again is 2R all squared, right? The distance, correct?
Oh, yeah.
And
So
therefore, we take all of these, both of these are equal to F to the force, right? To the force due to gravity. So now we equate both of these. We say, speak, please.
MSV squared over MSV squared over 2R equals to GME MS over 2R squared.
So now do it. Open these brackets. Go ahead.
Oh, what do you? Oh, you just want me to open them? It's just going to be.
Yeah, this.
Oh, you want me to expand them? What
exactly.
brackets? Oh, you want me to expand it? It's going to be 4 2R. Wait.
Yeah,
Just that?
2 squared is 4, right?
No,
right?
I thought you wanted me to like to make. Yeah.
2 squared is 4. R squared is just R squared. So this is what you get. Now let's express all of this for the velocity. So the velocity, first of all, let's kill off those who appear twice here. What do we do? Who goes?
Pardon? Where?
Who goes here?
Oh,
Let's cancel. What cancels?
The 2R.
Okay, you start with 2R.
Oh no,
what do you say? You say
the 2R and the MS.
So 2R here. If you multiply by 2R, 2R goes. If you multiply by 2R, at least what happens? 1 will go, you remain with 2, and then here the squared will go, you just remain with R, right?
Yeah.
Right?
Yes,
you got it?
It's going to be V squared.
So
Yeah,
G M E. Ooh, look at that M. M E all over 2R, right?
Yeah.
So the velocity in the first situation will be expressed thus, right? Right?
Yeah, Mr. I'm just solving the thing.
All right, all right. Tell me when you're done.
I will.
But then again, we have the Earth. Why do I draw it so tiny?
I got how many sig figs did it want?
Here you don't have data, you don't have numerical data. So what they want you, they say, what by what factor? So you leave it like this,
Oh,
because you don't 2r. You leave it like this. Now let's move on to the second part of the problem. They say the altitude, if the altitude of the satellite above the Earth's surface triples means how many times?
3 times.
So it means that this r here, you'll have first the r of the Earth itself, then you'll have r here, and then you have r here, and then you have r here. So it tripled, right?
It did.
So
it
the
did.
satellite now,
I'm following.
even though it tripled, what is the total? What is the total radius now we are looking at?
6.
But please look at it. The radius, not
if
diameter.
I'm going based off of, oh wait, that's the
Analyze
if
from
it
the
is
center of the Earth. Just count.
3R.
Again, from the center of the mass of the Earth. So the radius starts from the center of the mass.
Oh, 4R?
Excellent. So that's it. So we'll do this equation again, these two equations. Only this time we have the new values. Okay, we don't even have to. So we can come here and say, we know that for the force in relation to the satellite, the mass of the satellite will depend on the acceleration, which is the velocity of the satellite squared over 4r, because the distance has tripled, but that of course includes the distance to the center of the Earth. That's how we analyze these bodies. That's why we do this, especially when they're circular, because the mass is concentrated in the center of the body. Now, we know again that the force will be equal to capital letter G. Speak to me.